Go ahead, I was just.
All right, recording started. And can someone
Alright.
share slides so we can just get started?
George will be starting with P1 with the broadcast slide. So once we start with P2, maybe you or Dennis can share the slides. Okay.
Cool. And there's Paricha. Cool. So the P1 can just go ahead.
Okay. Hello everyone. So this is the bootcamp for homework one. We'll be going over both part one and part two, just a general workflow of how you can go through the homeworks and do them successfully. Uh, we'll also be having some tips for part two because that involves a lot of experimentation with hyperparameters. We won't be going through each and every line of the handout because we expect that you would have read that on your own. And the purpose of the session is to guide you as to how to approach the homework more than how to exactly do it. So I'll be starting off with P1. Let me quickly share my screen for that. All right. Can you all see my screen? Can someone confirm if the screen is visible? Oh, okay, good. Okay. So first of all, for any homework that you get in this course, please choose read the handout. Please read the write-up first. You might be able to complete some part of the code if you directly dive into the handout, but you will not be able to understand what you are exactly coding. So it's better if you go through the write-up first. Beginning with the write-up for homework on part one itself, there is a checklist which gives you a logical sequential way of completing each and every part of this homework. So please follow this step. Please follow these steps. In general, what part ones are we are trying to build a library just like PyTorch, and we call it MyTorch. So in every homework, uh, part one, we incrementally add more and more features to the library. For the first part, for homework one, we will be adding linear layers, activation layers, loss functions, optimizers, and some normalization methods. As you might have understood from your lectures already, these are the fundamental building blocks for a simple feed-forward neural network, which is kind of outlined here in this figure on page number 10. So this is what we are trying to build in the first homework. Just backing up a bit, to get started with this homework, you need to set up your environment using the requirements.txt file, which is attached in the handout. There are also some instructions on installing Anaconda if you haven't done that in the appendix, so please go through them. The important part of this homework is the autograder, which is responsible for checking whether your code is correct or not. You can also partially check your code by specifying which parts you want to test in the homework on autograder flags.py file. So if you go to the handout, there are these flags. You can set whichever ones you want to true. And in the end, after you've completed all the code, just set all of them to true and run your local autograder before submitting to AutoLab so that you can confirm that your code is working fine. Um, and final thing before I get into the individual sections, please do not use any other advanced libraries like PyTorch, TensorFlow, etc. The only things that you will be using are NumPy and possibly SciPy or math. So please restrict yourself to using those libraries. We'll be implementing all the machine learning operations using these linear algebra libraries. Cool. And there is also some notation given here, which will be followed throughout the write-up. So if you're confused or lost at any stage of what does some notation mean, please go back to this page to refer to it. That will help you understand what library methods you have to use to implement which formula. Right. So the first section that you will be implementing is the linear layer. So the linear layer, as you might have learned from the lectures, is just an affine transform on the inputs. So you have to implement the forward and backward method of this layer. Please read the theory which is given here, specifically the backward method, and understand the shapes of the different matrices involved in different parts of the linear layer. This table given here would be really helpful in you understanding the shapes and also being able to debug in case you run into shape mismatch errors in your code, because you might end up in a position where you're multiplying matrix A and B, but you actually have to multiply matrix A and B transpose, and you will be able to debug such errors only if you print the shapes of these matrices and compare them with what is given here in the table. So yeah, please go through the story given here to understand what you have to code before you actually start coding it. Talking about the code itself, uh, I'm sorry. In the forward method, you have to implement this affine transform of the inputs, which is pretty straightforward. For the backward layer, you have to implement a few backpropagation derivative mathematical formulas, which are given here. Uh, these are simple implementation of chain rule, so you can just read through them. I'm sorry. You can just read through them in this paragraph how these are derived. And talking about the implementation itself, you just need to be concerned with the final formulae that you have to implement. Going to the handout for the corresponding section, if you go to the linear.py file under mytorch.nn, you will see that there is some starter code given here. You can code it from scratch as well, but there is some starter code given here for your help. Uh, the places where you have to fill in your code have been tagged with to do, and there are comments also to help you along the way. So once you have an understanding of the write-up, you'll probably be able to fill in this code pretty easily. The next part that you have to do is activation functions. So as you must know, in a multi-layer perceptron, the linear layers are responsible for doing all the linear affine transforms, and the activation functions are responsible for adding non-linearities to the MLPs and thus modeling more complicated relationships. So for the purpose of this homework, we'll be implementing four scalar activations: sigmoid, relu, tanh, and gelu, all four of which are given here in this figure, and one vector activation, which is softmax. So I suppose from your last lecture, you know the distinction between scalar and vector activations, which is mostly in how they operate on inputs and how they backpropagate gradients. Before you go into the individual activation functions, please make sure to read the description, the broad description of the forward and backward methods here, particularly the backward method, because the backward methods of vector activations are quite involved. So really encourage you to read through this to understand what you'll be coding. Once again, there's a shapes table here that you should be referring to whenever you run into any errors. Then talking about the individual functions, scalar activations are pretty straightforward because you just have to operate element-wise. The only difference between all the four activation functions is the exact formula that you have to implement, and those formulae are outlined here in the respective sections. In the GENU function, the math is a little more complex, but again, you don't really need to be you don't really need to be concerned with how you derive the final equations. You just need to be concerned with what those final equations really are. For those who are slightly more mathematically inclined, I'll encourage you to look into how we solve this integration, how we differentiate this product, which is the GELU equation itself. But again, for the implementation point of view, you just need to look at the final functions and see what library methods would help you implement them. Finally, coming to the softmax activation function. As I said, this is a vector activation function and hence is different from the previous four scalar ones. So, but the final equations themselves are pretty simple. Uh, you might not be able to implement it in a vectorized manner, so you can just use a loop which I'll be just showing you in a second. But yeah, just going through the theory here would suffice to implement those functions. Going to the activation.py file, there's a model scalar activation function which is mentioned for you here, which is the identity function which basically replicates the input into the output. You have to follow a similar pattern for all the scalar activation functions. You have to create a forward and backward method, save some things in the forward part to help you calculate the backward method. That is why the skeleton code is not given for the rest of the four scalar activation functions. You can follow a similar pattern as the identity function does. For the softmax, though, there is a lot of starter code given here, and you just have to fill in the blanks where the to-do tag is given in accordance with the write-up and the comments mentioned here. So this should also be pretty straightforward if you get a good understanding of what vector activation backward methods are. I'll just take a pause at this moment to check if there are any general questions. For any specific code-related questions, you can come to the OH or in the hackathon. But if there are any general questions about the homework, I can take a pause right now. Well, I'll take that as no questions. Right. Coming to the next part, it's building neural networks. So this section builds on the previous two sections. You are basically convolving linear layers with activation layers to build multi-layer perceptrons in this section. In particular, you'll be building three network architectures. first one is a simple input-output architecture, which we call MLP0 because it has zero hidden layers. It looks something like this. There's an input layer and an output layer. Then there is MLP1, which has one hidden layer. And then there's MLP4 with a few more extra hidden layers, which is this particular architecture that you have to replicate. The math for the forward and backward methods is given here, but in practice, when you code, you will be able to reuse the forward and backward methods of the activation linear layers that you had defined in the previous two sections. For each of these MLPs, you have to implement their own forward and backward methods in terms of the layers that you're using. For that, once again, there is some skeleton code given here. It resides in models.mlp.py. Each network basically has a list of layers. It is an alternating list of linear and activation layers, whichever activation you have to use. And inside the forward method, you iterate through these layers, keep calling the forward method, each layer taking as input the output of the previous layer. And then on the backward method, you iterate through the layers in reverse order and backpropagate the gradients from the last layer to the first layer using the backward methods of the respective layers. For MLP0 and MLP1, you can just code the steps in separate lines, but as you get to a larger number of layers in MLP4, you will be needing a loop to iterate through the layers, which basically makes the code more modular, where you can just throw in any list of layers and it will keep working seamlessly. So all this framework of the loop and everything is given here. You just need to fill in the correct forward and backward method calls to the respective layers to be able to complete this part. At this point, I'll hand over to Shadrach to cover the rest of homework one. Shadrach, do you want to take over?
Yes. If there is some questions maybe to this part, they can ask before proceeding with the other part. Yeah. You're on mute. You're muted.
Oh, I'm sorry. So I was just saying that from one homework to the next homework, you will also have to copy some files over. It's highly encouraged that you anyways keep everything on your local PC instead of some cloud environment where very difficult to work with non-notebook files. I'll stop sharing.
Yeah, let me just share my screen. Hi everyone. I'm going to continue with the part for the losses, optimizers, and also regression techniques like memorization techniques. So let me just put on my screen. So we'll be starting the part for the loss. As I'm seeing that we have a part for this homework, also we have the chance to implement the loss functions. And for this part, we'll be implementing only two loss functions for this homework, part one. The first one we'll be implementing the mean square error loss function for this part. The only thing you need to do, you need just to follow the formulas that has been given through the write-up. Just follow these different formulas, and it will be easy for you if you just follow them. And also try to go back and read the notation symbols that have been given through the write-up so that you can be able to understand those different operations that's being given here. For the loss functions, you need to implement both the forward method and also the backward method for these loss functions. Maybe just look into the side. You can see that For the loss functions, also we have the main class for the main loss function. So for this part, the only thing you need to do, you need to implement those to-dos for both forward method and also for the backward. So for this one, you expected to return some returns from after implementing the backward. You need to do some return here. And also for the forward, also we expect you to do some return here after implementing all the required to-dos here. The other loss function that we'll be implementing for this homework, we'll be implementing the cross entropy loss.
Cedric, if you're sharing any code, we cannot see. We can only see the writers.
Oh, really? Sorry. Okay, so can you see my screen?
Yep.
Yeah, great. So I was saying that for the loss functions, also we have different classes for the loss function. We have the class for mean square error loss function. This is where we have different to-dos that we expect you to implement, and after that we expect you to return something here, which is said not implemented. So we expect you to return something here, which is probably this mean square error after implementing that. You'll be also implementing the backward for this class and also expect you to return something here. So also we'll be implementing also the cross entropy loss, as I said. Also this function, this class also has the forward method and also it has the backward method. So you can see that you have different to-dos. And also for cross entropy loss, it's both combines the softmax activation function, if you can see here. So after implementing all those to-dos, then we'll be ready to go. The other part we need to implement for this part also, we'll be implementing the optimizers. But for this homework, we'll be implementing for part one, we'll be implementing the stochastic gradient descent for this homework, but you'll be having the chance also to work with the other optimizers in the part for the bonus. So you have different notations here, which implements different parameters. So you can go through the write-up so that you can try to understand different parameters required here, so that you also can understand what we'll be implementing for this part. Mostly for gradient descent, what you need to implement is the step function or the step method for this class. Let me just bring up my screen again. For stochastic gradient descent, we'll be implementing this part. Those to-dos for here, there's no other thing you need to implement except this step function. You can see that we don't expect you to do return for this function. No return required here. You just implement the to-dos, then we'll be done with this part. The other part that we'll be implementing for this homework part one, it is the batch normalization for one dimension. So be given also the chance to implement the one of the legalization technique, which is batch normalization for one dimension. It has also the forward method and also the backward method. For the forward, you have different to-dos to be implemented here. And also for backward, also have some to-dos to be implemented here. And so you can see, we expect you to return something from both backward and also for the forward methods. So reading through, for batch normalization, it is quite difficult. But if you go through the write-up, it will be easier for you. So that's why I recommend you to read carefully the write-up so that you can understand it clearly. You can look at through the write-up. Those are different parameters. Please try through those different parameters, all those variables, and try to understand it, and also try to understand also the different operations that are being carried there. Once you continue down, you can see different parts for this, and those different formulas for backward and also for the forward. So this is all for the part one, for the homework part one. Except if you have some questions, you can ask them so that we can try to see if we can answer them. Welcome.
Swarm tends to be the most difficult part of this homework with a lot of operations and each operation creating a different, a new variable at every step. So the dimensions table will be particularly useful for batch normalization in case you end up stuck in some place.
Yeah. So then if there is another question, maybe you can just hand over to Josh so that you can proceed with the part two for the homework. Josh
I
or
wanted
Dennis?
to ask why we're not returning anything with the step class in the optimizer.
The step
Yeah,
function
so for the
is-
step function, the step function is only for updating the model parameters. That's the reason now you don't need to do any kind of return. Stochastic gradient descent, it's only for updating the model parameters. So if you do some kind of the update, then those updates will be applied automatically to the model parameters. So that's why I don't need to do any kind of a return.
Okay, that makes sense. Thank you.
Welcome. Over to you, Dennis.
Josh was supposed to go first. I'll share the screen with the slides. Can you see my screen?
Yes, Dennis.
Josh, can you go ahead?
All right, so we'll just get started with the P2 portion of this. So in a nutshell, what we want you to do with P2 is for homework 1 part 2, we're going to provide you with a data set of audio recordings, and then the write-up is going to explain more of it, but the gist is we want you to predict the phoneme labels with each data sample that you're going to receive from there. And of course, you're going to build a deep learning model. And at this point, all you're going to do is to just build a multi-layer perceptron that's as deep and as wide as you want, without using any sort of more advanced tricks that you will learn later on in the semester. So the typical workflow from this is that we will host this competition on Kaggle. I don't know if you guys have experience with Kaggle previously, but then in short, this is just a platform where you hold data science competitions, and then you're going to download the dataset from there. And in the end, all we want from you is your submission to the Kaggle competition. And it doesn't matter how you achieve that submission. I mean, obviously, I have to abide by the policies, but then normally what you do is you write a data loader, you load the data set that you download from Kaggle into that data loader, and you do a bunch of ablations, which means you try to find out what set of hyperparameters or model architectures or other things are the most beneficial for performance on this particular data set. And you train the model using the hyperparameters that you set, and you test the model on the test set, and you iterate this process for a couple of times to find the optimal hyperparameters for this process. And in the end, you just use the best set of hyperparameters to generate a set of submission phoneme labels, and to submit that set of labels, which is the prediction for the test set, to Kaggle. So this is in a few sentences what we want you to do for the part 2 Kaggle competition. And then this is the point where you go to the next slide.
Hey, sorry, there's a fire drill in my place, so I'll have to leave. I think Pavitra will cover for me, or you can go ahead with the rest of the part.
Excuse me, I didn't hear that. Why did the screen record, the screen?
There's a fire drill around my place, so I'll have to leave. So could you please cover for
You
me?
can continue the data and I'll go ahead with the ablations. I'll just share the screen though, just a second. I think this should be. Yeah.
All right, we can pick up from the data slide, which is, yes, it's here.
Oh, would you be continuing data? Then I'll take up the ablations or.
Wait, so Dennis, you said you need to go?
He's not able to, so he just suggested you could continue.
Okay, cool. All right, I can cover for that. So, basically, what happens with the data section is you can download a lot of what's called raw speech signal pre-processed in the form of MEL spectrograms from the Kaggle competition. And then what we did to the raw speech signal is called short time Fourier transform, but then that is actually not terribly important for the purpose of completing the homework. So you can read more about it. There's more explanation of this in the write-up, but otherwise you can go to the next slide, please. We can just concern ourselves with the higher level features of these audio signals, which are called phonemes. So literally a phoneme is a subsection of the speech that we concern ourselves with. And there are this many phonemes that we think that exists in this homework. So all of them, you can pretty much understand. The SIL stands for silence, and the SOS stands for start of segment, and the EOS stands for end of segment. So these are markers that you place at the start and end of each segment or sentence to fully translate whatever audio segment that is to a transcribable text. All right. Next slide, please. All right. So what happens with the dataset is you will need to write in this format. This starter code is actually provided to you, but the PyTorch convention is you will write a class that is a subclass for the torch.utils.data.dataset. So in there, you will need to subclass, or you will need to override the three methods, which is init, getItem, and getLen. So the init is where you take in as many parameters as you want, but then you will need to supply the, for example, the directory where you hold these files and the transcripts, and then you do these pre-processing steps for the dataset to be able to supply the particular input features to the deep learning model that you are building. So keep in mind that the dataset is not part of the deep learning model, but then it's up to you to design the specification or the interfacing between the dataset and the actual model, as long as they can work with each other, right? So, Pavitra, do you think we need to explain all of these code line by line, or?
No, I think that's fine. So more about all of that, as Harshad mentioned, do read the write-up. It is very important for every homework, and do start early. Coming to that, this is where your study groups would come into picture, and study groups are really important here, and you all have to run ablations. And just a second. So this is an example of how you all can do ablations when it comes to P2. So there are a lot of hyperparameters which have been given on the write-up, you all can divide and segregate it among the 4 of you in the study group and plan like who would do what, and then note down your readings. This will help you get an idea of what works better for you for the like for which model is working at like which with what dropout, etc. So you could experiment with various types of ablations, and this would help you for the high cutoff. So like once if like one person, like the whole team would be doing ablations and noting it down. So like even if you know that okay, a model is performing well at a certain given hyperparameters, you all could try to work on it further for the high cutoff. And that being said, you all can log your ablations on WANT-B, and this is how it would look when you all run on the same project. We do recommend you to run it together because you could like it's easier to visualize, and later there's like an optional link where you can submit the ablations. And so when it comes to ablations, don't just start with everything together. Start slowly, understand what hyperparameter is working better, or at initially if like some model is giving like if it's not performing at all in a few epochs, you could like try experiment something else and so on. And do read about how the hyperparameters are working so that you know okay like why it is not working or why it might work with your particular model. And there are multiple architectures given in the write-up. You could divide that everybody tries different architectures so to know which works best. And reaching the high cutoff would not be easy, but if you all perform ablations pretty well, it'll be doable. So that's I think pretty much for part 2. There's also an MCQ which has homework 1 and homework 2 together, which is also due next week. And I think study groups would also be finalized by next week. So the deadline for the homeworks are 2 weeks later. So but we do recommend you all to start early, and we hope that all of you fill the study group forms. So yeah, I think that's pretty much
There's
it.
also an early deadline on 14th by when you have to make a mandatory submission to clearing the very low cutoff for part 2 and submitting the full paper with those documents. So beware of the early deadlines.
Harshit just told that it is mandatory to do a submission for P2 before the early deadline, crossing like the very low cutoff. And we'll post the high cutoff and other details in the coming few days.
This is also due on 4th.
You could start working on both of them simultaneously, a bit by bit, because there is like if you submit the homework 1P1 before the early deadline, there's a bonus for that as well. But yes, we do recommend starting P2 early because the model training would take time, definitely. I think Harshit can add on to this.
Great. Just complete whatever code you have to fill in the P2 notebook and start your ablutions because it will time. And once you've started doing ablutions, it is a lot of passive work. So you can keep working on P1 parallelly.
I think there's a question in the chat asking about early submission. So you need to make a submission before the early deadline with at least a 55% to get that for the early submission. So just that you're aware. Okay, the other thing I wanted to say that this early submission is mandatory. So if you don't make it, you will miss out on 10 points. So there are 10 points which you get by making the early submission that passes at least 55% and by answering the quiz that's on Canvas. So make sure you make that early submission and do the MCQs.
We are mostly done for the meeting. We're just waiting if there are any more questions. No, cutoffs are released before the final deadline. For the time being, you just know the super low cutoff, which is what you have to clear by the early deadline. But the other cutoffs, like the low cutoff, medium cutoff, and high cutoff, will be released in the coming few days. But that will be before the final deadline occurs. Only deadline is on Autolab for P1, but it's not mandatory to complete P1 by the early deadline. There are just some bonus points if you complete it by then. But the Kaggle early deadline does apply to P2 uh, with regards to the very low cutoff, 55%, and also the Canvas quiz. Yes, yes, that's right, as John. Yeah. I think then that's that for this meeting. We can take any other questions on Piazza, and there is also hackathon this Saturday where you can come and code with your study groups and ask questions to peers.
There's a question about the study groups. I think
They'll be assigned next week. So the last day to fill the form is, if I'm not wrong, 11th September. So yeah, after that, it'll be assigned to you.
I think if there are no more questions, we shall end here.